Okay, so let's take one example here. Okay, so for this scenario, we're going to imagine that we flipped a coin 200 times. And when we flipped that coin 200 times, we got 120 times it landed heads up. And 80 times, thanks Kevin, landed tails up. Hello, come on in. Yeah. All right, so these are observed values. So what we want to know is that we're going to perform a chi-square test on those results to see what we get. So first of all, we're going to identify outcomes. For this example, there are only two outcomes, right? You can get heads or tails. Only two outcomes. Then we're going to identify what our observed values are. So our observed values, we got 120 heads up, and we got 80 tails up. Our expected values. What would be our expected values for this scenario? What do you think, Lindsay? Yeah. Yeah, it should be 100 and 100, right? Assuming 50-50 chance, should be 100 and 100. Right? So, what we want to know is whether or not the differences between the observed and the expected here are just due to random chance or if it's statistically significant, right? So we're going to perform this quick calculation here. So we're going to take our observed minus our expected. We're going to square that, and then we're going to divide it by our expected. Okay, so I get 0.4, 0.4 for both of those, right? Are we tracking with me? Annika, you got a question? What's up? How I calculated that? So I did 120 minus 100, that's 20. Whoops, that should be not 0.4. What should it be? 20 squared is 400 divided by 100 should be 4. My mistake. Thanks for that catch, Annika. Should be 4. It's fifth period on Friday. Yikes. Okay, so I've got 4 and 4. Does that make sense now, Annika? Or did that confuse you even more? Oh, I'm so sorry. I'm so sorry. So what I did is I took my observed value for heads, which was 120, and I subtracted the corresponding expected value, which was 100. Then I squared that and divided by the expected value again, which was 100. Yeah. Yeah. Sorry about that. I misunderstood your question. Okay. So then for a chi-square, again, you're taking the sum of those calculations. So our chi-squared value here would be 8. Okay. So our chi-squared value is 8. Our degrees of freedom. How many total outcomes were there for this scenario? 2, right? So 2, so my degrees of freedom will be 1, right? So I've got my chi-squared value. I've got my degrees of freedom. My p-value will always be 0.05. So let's go find the critical value. So the critical value I've got the table right here, actually. So, p-value is 0.05. Degrees of freedom is 1. My critical value is 3.841. So, I exceed my critical value, which means that I reject my null. So my critical value was 3.841. So I reject my null hypothesis because chi-squared was greater than my critical value. Okay. So what that means is you probably have some type of weighted coin. That's not a fair 50-50 coin. It tends to lean towards heads when it flips. Okay. How are we feeling about this so far? Did that help kind of put it into context of what we're doing? Okay, so that's like just a straightforward probability problem. Let's do a genetics problem. Okay, so a genetics problem. Want to get a question? What's up? One more time. DF, sorry, degrees of freedom. Degrees of freedom, which is the number of outcomes, which is 2. Minus 1 gives you degrees of freedom of 1. Yeah. Okay. So, second one. Let's do a genetics context. So, for this one, we're going to say that for a particular species of fly, red eyes is dominant to white eyes. Okay, and I'm going to use capital R to indicate my dominant allele and lowercase r to represent my recessive allele. And what I did is I took 2 flies that were heterozygous for eye color, meaning they had that genotype, one dominant, one recessive. What would be the phenotype of both of those flies if this is complete dominance? Would these flies be red-eyed or wide-eyed? What do you think? Red-eyed, right? So they have a dominant allele, and since this is complete dominance, you'll get red eyes. What's up?
Can you define phenotype?
Yes, phenotype.
I just don't remember.
All good, thanks for asking. So phenotype, this is, in this context, the form of the trait that is observed. And genotype is the combination of alleles that they have for that trait.
Homozygous.
You got it. Okay, so the genotype for these two are heterozygous. The phenotype are both red. This is also referred to as a monohybrid cross. And what was observed was there were 420 red-eyed flies. And 280 white-eyed flies. Okay, that was what was observed from the offspring. Okay. So, with that in mind, we're going to do the same thing. So my outcomes. Kevin, how many possible outcomes are there for this scenario? What's that? Sorry, say that one more time. You say 700? 1,200? Where are you getting 1,200? 700. So you're referring to how many flies? 2. 2, 700, or 1,200? 2. Okay, yeah, 2 to 2. You got it. All right. 2 outcomes. And Kevin, what are those 2 outcomes? Yeah, you got it, right? So the only 2 outcomes are red eyes and white eyes. All right. So I'm going to take my observed. I observed 420 offspring that had red eyes and 280 that had white eyes. How do I find my expected values? Well, first of all, like Kevin mentioned, there are 700 flies that were observed, right? How do I find my expected value? So it will be 350, 350. Talk to your table real quick. What would you do to find the expected values? All right, we ready? So, Cindy, what do you think? Divided by 2, so you would get 350. So that would be the expected for red eyes and expected for white eyes. Okay. So 350, what that would assume is that there is an equal chance of the fly getting red eyes or white eyes if they're an offspring of this cross. All right. How do we determine the probability of phenotypes? How do we determine the probability of phenotypes? Here's a hint. How do we determine probability. So if we were to do a Punnett square, I know this is reaching far back, right? Far back. If we do a Punnett square for this monohybrid cross, what would be the possible combination? So we would have parent 1 here, parent 2 here. We know that the parents can only pass on one allele to their offspring, so the possible combinations are this. Right, assuming that it's a 50-50 shot of which allele is passed on from each parent, these are the possible combinations. But which of these offsprings will have white eyes? What do you think? Yeah. 25%, specifically this homozygous recessive, will have white eyes, right? So, Cindy, if white eyes is 25%, what's the probability of red eyes? 75, right? So 75% will be red eyes. So we can actually use that same strategy that Cindy was talking about. We're going to add up those values to determine we have 700 flies, and we're going to multiply that total by the specific percentage that we'd expect, right? So 700 times 75%, what is that? 525?
245. Wait, the
75%, sorry.
oh, it's
525, right? And then,
the other one.
wait, 245?
Oh no.
175, 175. It's all good. We're all struggling, it's okay. All right, 175.
175.
Does everyone see how I got that value? Yeah? Okay. So, what I want you to do at your table, I want you to calculate the chi-squared value for this scenario. So in that next column, go ahead and calculate the chi-squared value for this scenario. like 1 more minute or so. All right, let's see what we got. So, Sarah, what did you get for this calculation for red eyes right here? That's okay. You got 21. Give me a thumbs up if you got 21 as well. Yeah, looks like you got some consensus. Yes, this should be 21. Right there, 21. If you got a significantly smaller value, make sure you squared your value here. Okay, how about for white eyes? Sarah, we'll go back to you. What else did you get for white eyes? You got 68? 63. Give me a thumbs up if you got 63 as well. Okay. Raise your hand if you got something else besides 63. Milani, what'd you get? 39.375? Yeah. Any other values besides those two? So, let me double check. I got something else. So, 175. Yep, 63. So the mistake that I made, was I divided by the same expected values that I used for red eyes. So you might have noticed that the difference between the observed and expected values were the same for red eyes and white eyes. It was both 105. And so it's important when you divide by your expected value to make sure you're dividing by the correct expected value. So actually, when I did mine, I got 21, but I divided by 21. Right? So it's making sure that you have the correct expected value. So 63, that means our chi-squared is what, Jovito? What's our chi-squared? 84. So chi-squared is 84. Let's go to our degrees of freedom. What's our degrees of freedom again? Should be 1. Right, we have two outcomes again, so our degrees of freedom will be 1. P-value is 0.05. So we actually will have the same critical value, which is 3.841. Do we reject or accept the null hypothesis? We reject, and we kick it to the curb. It's very clear. We've rejected it by a large margin. So, reaching back a little further, what could account for that? Reaching back to